And those Q values are going to be the same everywhere apart from the states and actions that I just visited. So we only update those Q values along one trajectory, but that's already enough to change the behavior that we actually see there. So in practice, if you're actually writing this, you don't need to explicitly store pi, you just store Q, but when you actually come to select actions, you always just look at the freshest, most recent Q, and you flip a coin and you either pick the maximum Q or you pick a random action. So this pi is kind of implicit, and all you need to remember is your 1/k schedule that you're using to determine the bias of this coin that you're using. And this algorithm actually finds the optimal action value function. So this is really, this is our first full solution. This is something which you throw it into any MDP and you just let loose with this thing, and it will find the right solution. And it's considerably more efficient to run it in this way, where you actually update the Q values every single episode. You update your Q values and then immediately improve your policy, rather than having to generate a whole batch of episodes, thousands of episodes, to just get one evaluation of Q. So this actually works much better in practice. Okay, are people clear about this algorithm? Like the idea? It's a good time to ask questions if you're not, so we're just going to keep on adding to these ideas. Okay, good. I'll take silence to mean comprehension. Okay, question.
I can't remember if you addressed this in an earlier lecture, but is there any particular idea behind the initialization of the values for Q, or do you do random initialization?
Okay, so the question is, does it matter how you initialize Q? And in terms of the theory, you can start with anything. It will still converge. In practice, of course, it helps to have a good estimate of Q. The closer you are to the optimal Q values, the faster this thing will converge. It's a bootstrapping. Sorry, it's not bootstrapping like with TD, but still, we're basically starting from these Q values, and we're updating incrementally from. Actually, sorry, that's not true with this particular schedule. Let me back off that. We'll see that for later versions where we have an incremental update. So for this particular algorithm, it makes no difference because we're just taking the mean, and so the very first time you see a new state action pair, you will replace any Q value that you started with completely, because n will be 1. You completely replace your old Q value with that return that you saw.
Right.
So for this particular algorithm, it makes absolutely no difference what your initial Q values are. In practice, and in the rest of this lecture, we'll see algorithms where you don't have this perfect mean, but instead you have some non-stationary estimator that has something like a constant alpha here. And for those algorithms, it matters much more what Q values start with, because you're incrementally moving on from that initial start value. And then your start value, the closer you are to optimal, the better. So, yeah, sorry. Correct myself there. Okay, question. Then I'll move on.
You said it's more efficient to update for every episode.
Yes.
But if you do it for many episodes, you have the chance to parallelize the process, so you run a lot of episodes in parallel.
Okay.
The same value function, whereas
So that's a great
with this
point.
you
So
have to wait.
So I guess, yeah, I'm just focusing on serial computation for now. There are many possibilities for exploiting parallel computation, and you're right that you would want to, that parallel computation introduces constraints on what you can and can't do, and you may want to, it's almost, I think the same is roughly still true with parallel computation, that you still want to use the freshest possible Q values that you can, but with parallel computation, those might necessarily be a little more stale than the very latest episode to come in, because you simply don't have access immediately to all of that parallel computation. Okay, so let's just do a quick example. So we had this Monte Carlo example in a previous lecture. In last lecture, we just looked at evaluation. We basically said, okay, if I send you into a casino and I tell you that you have to stick, basically unless you're always going to ask for a new card unless you're on 19 or 20 or 21, I think was the policy we had before. And then I want to know how much money would you win or lose in that casino. So that's what we looked at before, and we had a particular plot of the value function, and it had a particular shape to it. And now what we're doing is we're actually running this algorithm we saw on the previous slide to generate the optimal value function. So now this is the question you probably really want to know, which is, if I walk into a casino, what policy should I play to get the maximum possible amount of reward? And again, real casinos use slightly different rules, so don't try this. But I'm not responsible if you lose all your money. And so this basically tells you, now we've run our Monte Carlo, we've iterated through several processes where each episode we update our value function a little bit. We actually store Q internally, but just to make the plots easy to look at, we're now basically summing over all of the actions to estimate V star from our Q. So you basically have some Q, that generates some epsilon greedy policy, and then you alternate backwards and forwards by running these episodes just like we saw in the last algorithm. And you end up with a policy which looks something like this, which says that if you don't have an ace in your hand, you should actually have this quite interesting looking policy, is the optimal policy to follow, where depending on what the dealer has here and what cards you've got, there's this threshold somewhere between like 16 and 17, where if you've got 16 or less, it's better to ask for a new card. But there's some situations where a dealer has some kind of quite difficult card to play with, where there's a high probability the dealer will go bust, in which case you should probably just stick anyway and just wait for the dealer to go bust. Okay, so you kind of vary your policy according to that. If you've got an ace in your hand, of course you can afford to ask for more cards more often, because that ace can either be a 1 or 11. And then this is what the value function looks like. So it's just a continuation of that last example to show you that this process really does end up with usable information, in the sense of you get these nice shapes out of these value functions that really characterize exactly the optimal behavior in this domain, and you really end up with something which is the optimal policy. There's no way to do better than this in this particular game that we've described. This is the optimal way to behave. Okay?
Why would you ever stick at 11? Because you can't go bust.
You wouldn't. It always says to hit on 11.
When dealer is showing between 4 and 6.
So this line here says if you're on 11, you always hit. This
Sorry.
region here.
So the line is between 11 and 12.
So it's like a grid, and each cell of this grid is indicating what to do. So this could be shaded in if you like.
Yes, yeah.
And showing you for 11, you should always hit. But if you've got 12 and the dealer has a bad card, there's some chance the dealer might go bust, and so you should just stick on that 12 sometimes. Okay. So we're now going to move on to temporal difference learning methods. So just like the last lecture, we kind of split things between Monte Carlo learning, and then we moved on to TD learning, and then we saw that there was a spectrum in between these two things. We're going to follow the same process now, but with control methods rather than evaluation methods. We're really going to try and understand how can we actually gain efficiency by bootstrapping, by using the same tricks that we saw last time, and gain a lot of the efficiency. We want to basically use TD. Why? Because it can be lower variance, because it can be run online in continuing domains. Even if there's no termination, you can still run this. It can be run from incomplete sequences. And what we'll see actually in this lecture is that there's an additional benefit to using TD, which is when you use off-policy learning. It becomes particularly important to use TD. And so the natural idea, well, let's try the obvious thing, which is use the same generalized policy iteration strategy. But we know that to do model-free policy iteration, we need to use Q. We need to use Q so that we don't have to do any look-ahead in our to do our greedy or epsilon greedy policy improvement. And the idea is basically to use now TD learning to estimate Q. So let's just slot in TD learning in place of Monte Carlo policy evaluation, and continue to use epsilon greedy policy improvement. And that's immediately going to give us an algorithm that we can apply, which is probably the best known algorithm in reinforcement learning. And the only difference we're going to do is because TD can operate at this higher time scale. So TD learning is something where you don't need to wait until the end of the episode to update your value function. In fact, you can update your value function after just one step. That's one of the advantages. It's online. Like you'd see one step of data, you bootstrap, you update your value function immediately. And so again, if we follow this general principle of always using the freshest, most recent value function to pick your actions, what we're going to do is we're going to increase the frequency of our policy improvement to be every single time step we're going to improve our policy. So the general idea is called SARSA. So why is it called SARSA? Well, this diagram should illustrate it. We're basically starting off in some state action pair. That's this black dot, the decision node. We're basically choosing an action. We're going to randomly sample our policy. So we're going to see a reward R. We're going to end up in some new state S prime, and we're going to sample our policy again to generate A prime. So there's two steps of sampling. Sorry, we're not sampling our policy yet. So we start off with state here. We're asking a question about this state S and this particular action A. We're going to sample from the environment to see what reward we end up in and what state we end up in here. And then we sample our own policy at that next state. So we end up with SAR S prime A prime, or SARSA algorithm. Okay. So SARSA basically indicates a particular update pattern that we're going to use based on SARSA here. And so what do we do? Well, we're basically going to start with our Q values. We're going to move our Q value a little bit in the direction of our TD target, reward plus our discounted Q value at the next state, minus the Q value of where we started. So again, it's like I was in some state and I'm considering taking some action. And what I want to know is, if I actually take that action, look at the reward I got, and then the value of the next action which I would take, that gives me an estimate of the value of this policy, and I'm going to use that estimate to update the value of the state action pair I started in. Okay, that's the general idea. This comes from the Bellman equation for Q. We've seen this, hopefully, before becoming familiar with these type of ideas. So that's a SARSA update. Okay? So now we're going to take these SARSA updates and we're going to plug them in to our generalized policy iteration framework. So every single time step, we're going to move up and down in this diagram. Every single time step. So each time we take a step, we're going to update our value function by applying one step of SARSA. So for the state and action that we were just in, we're only updating the value function for that one state action pair at that time step by applying this update. So I was in this state action pair, I ended up in some new state action pair. I'm going to do one update to my Q value for that single entry of my table. And now I've already changed my value function, right? Something's different. If I end up back in that state action pair again, which I might in some loopy environment, I want to make sure that I use the latest, most interesting, most up-to-date, best information that I've got from my policy evaluation. So every single time step, we're going to improve our policy as well by acting epsilon greedily with respect to the latest value function. So again, what does this mean in practice? It means that you're just storing Q in your memory. You've just got this big table of Q values for all states and all actions. And every step when you actually come to take an action, you just flip a coin, you look at your Q values, and if it comes up heads, then you look at your Q values and pick the best one. If it comes up tails, you explore randomly. So the policy is implicitly represented by your Q values. And every single step, we're going to evaluate the latest action I took and update my policy just for that one state action pair. Okay? So we've really got this very rapid process of evaluating by SARSA and improving the policy. Okay. Let's try and get to know this a bit better. So what would an algorithm look like? So I think it's actually useful in this case to just maybe step through some pseudocode. It's really straightforward. So you can arbitrarily initialize this lookup table. Q is just a lookup table. In subsequent next lecture, actually, we'll see how to generalize beyond these naive lookup table representations. But for now, it's just a lookup table. Every state, every action has its own entry in this table. We initialize this arbitrarily, just say 0. Okay? And now we're just going to repeat. And every single step, this outer loop is just over episodes, but really, the inner loop is just every single step. We're going to take an action, observe the reward, observe the next state that we end up in. We're going to choose our action using our epsilon greedy policy. And we're just going to apply this SARSA update to that one step. So update a little bit in the direction of my TD target, the reward plus the discounted value of the next state action pair. And then repeat. So the next time we come round, we'll already have a different policy. because we're acting epsilon greedily with respect to our Q values, if I end up back in that same state again, for example in a loop, I will already behave differently using the latest and freshest information stored in Q. Okay, yeah, question?
S dash is chosen according to E epsilon greedy as well?
S dash is chosen by the environment. S dash is the next state. So state.
A dash.
Yes. So A prime. So the question was, is A prime selected according to the same policy? So A prime is selected using your current policy, and then you basically remember that, and now when you come in, you remember what your last A prime was. That becomes your A at the next step. So you just kind of remember your last A prime, and that becomes your new A.
How does that affect the equation? That you're choosing that, I mean, there's no reward coming from that last stage, right? The reward, the R that you're using there is from the intermediary stage.
Yeah. So the question is, why does this even make sense as an update, I guess? And so let me try and give some intuition. And I think the right intuition to have comes from the Bellman equation. That really what we're trying to do, this is just a sample of the Bellman equation. Like this right-hand side that we're moving towards, this thing here, this target, is a sample of the Bellman equation. We're basically saying what we want to do is we want to consider an expectation over everything which happens in the environment over one step, which basically is the reward plus whatever state you end up in next. So that gives you your expectation of the environment. And then and now we want to know, well, what would happen under our own policy? We want to know what would happen under our own policy after that point. We want the expectation under our own policy from that state onwards. And that expectation under our own policy is precisely what we're trying to evaluate with Q. So that's why it has to be evaluated. We have to select actions using the policy that we're trying to evaluate. This is an on-policy algorithm, fundamentally on policy. We're selecting actions and we're evaluating that policy. So SASA is an on-policy algorithm. Okay. So you should be wondering, well, does this work? And just like Glee Monte Carlo, this version of SASA actually will converge to the optimal policy. And the only thing we require is, again, Glee policy. So again, you could choose your epsilon greedy with this decaying schedule. That would be a valid choice, just to make sure that you continue to explore everything and that you eventually end up greedy. But you also need to be careful about the step size that you use. So you have to make sure that your step size, if you really want convergence, you need to look at stochastic approximation theory, and you need to make sure that your step sizes basically follow these two conditions. And all this tells you is that the step sizes are sufficiently large that you can move your Q value as far as you want. So you might need to move your Q value from whatever your initial estimate was to some very, very large or very, very low value if you're wrong. And this thing basically tells you that eventually the changes to your Q values become smaller and smaller and smaller. The changes to your Q values have to vanish and become zero eventually, otherwise you'll still have noise and jumping around in your policy. So that's just stochastic approximation theory. But really, when you do all that, if you do all the machinery correctly, this thing really converges. In practice, we don't worry about this, and we sometimes don't worry about this either. And SASA typically works anyway. That's an empirical result. But this is the theory, okay? So let's have an example. So this example actually is doing precisely that. It's throwing out this theory and just using a fixed step size and a fixed exploration rate. Let's see what happens. So this is called a windy grid weld. We're just trying to wander around from this start point to this goal. We can take any of these King's move operations, so all the diagonal moves as well as northeast, southwest. And the only special thing about this grid weld is that every time we take a step, the wind pushes upwards and pushes the agent upwards some number of grid cells which are indicated by this number at the bottom of the column. So there's no wind over these first three columns. Then you get pushed up one step when you move here, 2 steps when you move up here, 1 step here, and 0 here. So the optimal behavior is basically you have to take account of the fact you want to make as much progress as you can when there's no wind, and I think you end up kind of taking this route, we'll see on the next slide, something like that as the optimal behavior. You have to come back around to get back to the goal.
Would you want to just go down and then be blown up to the goal?
That's not optimal. if you try to go down, then what happens is you end up being blown up one again, blown up one again, blown up two, and you end up overshooting the goal. Okay, so so you can try to do that, but you don't hit the goal. So you're better to get pushed up against the ceiling, come back round from the ceiling after that point, and come back to the goal again.
But if you can go diagonally downwards, or
Yeah.
diagonally to the right, then those first three you can just go horizontally. The one, sorry, the where you're blown up one.
So maybe this is a version that just uses the standard moves then. I'll have to check that. I think this might just use standard moves, and that the wind blows you into a diagonal direction. You're right, that would be 2 in that case. So here is the diagram of the optimal policy. So this plot basically shows us what happens if we use the naive version of SARSA. So it's just something to show you that, this is the policy that it finds, which I claim is the optimal policy. You can check that offline. And this plot here basically shows the learning curve for running SARSA. And so this is exactly the algorithm we just looked at. And what this is showing is actually the number of time steps. So this axis here is literally time step by time step. And what we're looking at is how many episodes were actually completed in those number of time steps. So you can kind of see here that the first episode took 2,000 time steps to complete. It started off with no knowledge about how to do this, and so it's basically just doing a random walk, and that random walk is biased upwards, so it's not even as good as a random walk, so it takes a long time to actually stumble on the goal. But when it does, and this is really typical of reinforcement learning and these generalized policy iteration algorithms, when it does, the very next episode, it does much, much faster, and you get these exponential increases, because once it learns some knowledge, it can bootstrap from that knowledge and do better and better and better and better as it starts to learn things. So it immediately learns faster and starts to complete episodes at a much faster rate now, until up here you can essentially look at the gradient of this, and the gradient of this should tell you the path length which it's taking, which I think is like 14 or something, the ratio between this and this, which is the optimal policy. So most of the time it's behaving optimally, but this is still, because we're not decaying epsilon, it won't be completely optimal because it will still be throwing in the odd exploratory action. Okay? And that's why it's got this bobbly look to it. Okay, so now we're going to take the step that we took in the last class, which is we're going to consider the spectrum between Monte Carlo and TD learning algorithms. We're going to consider these eligibility traces and lambda variants of these algorithms to see if we can again get the best of both worlds, get the best of the unbiased behavior that you get from Monte Carlo, and also get the best, or at least control the bias, have a knob that controls the bias variance trade-off. And so the way we're going to do that is by start off by considering these n-step returns again. And so what we're going to do is consider these returns now, which are basically the one-step return looks at one step of real reward and then our Q value after one step. But we could also use the two-step return. We could have looked at one step of reward here, a second step of reward here, and then look at our Q value after 2 steps. Or we could do that for any number of steps all the way down to infinity, which is essentially Monte Carlo, where we look at the reward after 1 step, reward after 2 steps, all the way until the end of the episode, and we never bootstrap from our value function. Okay, so that was the idea of these n-step returns. And so this Q return we can define in the following way. We can define the Q return to basically be the generalization of this to any n. And n-step SARSA just does the obvious thing, where we say for each state action pair, what we're going to do is instead of updating towards the 1-step estimate of our value function using SARSA, we're going to use this n-step return as our target. So again, this means we're going to take our estimate of the value of taking action A in state S. We're going to update that a little bit in the direction of our n-step target. Okay, this is this sort of idea of the incremental mean, this non-stationary updates again. And this n-step target now is, essentially saying, well, I'm going to look at, 1, 2, 3 steps, and then bootstrap from my Q value, which represents the value of the remainder of the trajectory. I'm going to use that as my estimate of the overall value of the trajectory, and use that to update my value of the state I was in and the action I took from this starting point. And we can do this for any n. And so again, just like in the last lecture, we want to be able to consider algorithms which are robust to the choice of n. and which average over many different n's. We want algorithms which kind of get the best of all possible n. Yeah.
So I want to ask just for reminder. So the Q function represents like the estimate of the whole trajectory from ST in the using action 8, right?
Yes.
Not the not trying to estimate only the one step.
Yeah, that's right. So all value functions, so let me be clear about that. So all value functions, including v and s, are long-term estimates of the amount of reward that you get. So the definition of q is the expected total reward that you get if you start in state st, and then you take action at, and then you follow your policy for all subsequent actions.
Mm-hmm.
That's the definition of q. So it specifically is a long-term estimate. We never consider just these, like even when we talk about these n-step returns, that's just our target. It's still an estimate of the complete return, but we're estimating that by looking at n steps of immediate reward plus something which summarizes the remainder all the way out to infinity or the end of the episode of the remaining reward, all discounted by the appropriate discount for each step. Okay? People good with that? Right. So, let's make a lambda version of this algorithm. So, this algorithm is called Sasa lambda, very well-known algorithm. So what we're going to do is we can consider, first of all, just the update. Like, what does this look like before we talk about the full algorithm? And the idea is we're going to basically average over all of our n-step returns. So we're going to consider starting in this state action pair. The environment pushes me to this state. I take some action, and then I estimate my Q value here. And we're going to weight this particular return by 1 minus lambda. We're also going to say, well, what if I start in this state action pair? Environment picks a state, I pick an action. Environment picks a state, I pick an action. We're going to look at the Q value, add up the rewards along here, plus the Q value at the end of this, weight this by 1 minus lambda times lambda. So each time we're going to multiply by another factor of lambda. This 1 minus lambda is just like to normalize the whole sum to add up to 1. So we get this weighted sum of all of our n-step returns, where we basically are looking, we take more account of the trajectories which are of the shorter n, and then we progressively discount by another value of lambda as we increase n. So the main idea is to now make this average return. So we had these returns which were n-step returns, and now we're going to average over all n. And the way we're going to average over them is just by defining this weighting, just like over here. We're going to weight each n-step return by a factor of lambda to the n minus 1. It's just the normalizing factor there. And so when we make this lambda return, this is just a way to average over all of our n-step returns in some way that's A, computationally convenient, and B, takes account of all different n. Okay? And it has this lambda parameter that we can tweak, which can make us either more or less far-sighted in terms of how much we prefer the large n or the short n. Okay? And so this gives us, now we can plug this right into our update. And so again, what we can do is we can say, now I'm going to update my Q value. You know, I start over here, and now I'm going to consider a weighted sum for this Q value. I want to know how good is it to take this action. And I'm going to consider some weighted sum that takes account of my estimate based on my Q value, my reward plus my Q value from here, but also based on my reward plus my reward again, plus my Q value from here onwards. We're going to weight all of these things together, all the way up to n equals infinity. That's going to give us our Q lambda, and we're going to make that our target, and we're going to update our original Q value a little bit in the direction of that target. Okay, so that's the idea of Sasa lambda. We'll see an illustration in 2 slides. Just before we do that, I want to spend 1 slide just saying that this was the forward view. If you remember from the last lecture, there was a forward view and a backward view of how to use TD lambda. That with these eligibility traces, we can actually come up with a back. So what's the problem with this approach so far? So this is great. We've got something which lets us build a spectrum between Monte Carlo algorithms and TD algorithms. So we've got now a variant of Sasa that can look all the way out to the future. If we set lambda to 1, it turns into Monte Carlo learning. If we set lambda to 0, it turns into our familiar SARSA that we saw in the previous steps. So now we've got this control where we can choose, our bias variance trade-off in between and average over all of these things. The only problem is that we're kind of looking forward in time, that this isn't an online algorithm. It's not something where we can take one step, update our Q value, and immediately improve our policy, because we have to wait until the end of the episode to be able to compute our Q lambda. And we'd like to be able to run things online and be able to get the freshest possible updates immediately, and have this kind of clock ticking over every step of getting the maximum amount of our policy improvement by making an adjustment every single step and running online. We don't want to have to wait until the end of the episode. There might not even be an end of the episode. This might go on forever. So what we're going to do is come up with an equivalent, just like in the last class, by building up eligibility traces, such that when we sum up over those eligibility traces, we're going to end up with an update which is exactly equivalent to this one. And so the idea is very similar to the last class. We're going to build an eligibility trace now, but the eligibility trace is going to be for all state action pairs. So now we've got a new table, a table of our eligibility